everyone, so on to another investigation using FET. So this time what we're going to do is we are going to investigate how the resistance of a wire increases with length. So first thing I need to do, you need to be in the virtual lab one so that you can change the wire resistivity. So change it from tiny to lots. Okay, so now our wires, instead of being ideal perfect wires, our wires now have resistance. So what we're going to do is we're going to set up a circuit like so. So you're going to have the length of wire coming out, your ammeter, another length of wire coming down, and then a big long length of wire like so. You want to try and make this wire down the bottom here, from here to here, as long as you can. And what you can see straight off is that by changing the length of this wire, we're changing the current. Now, when you're doing this at home, you can put a ruler up on the screen, a physical ruler. Obviously I can't do that because I don't have, or you can't see it then, so I've got a ruler app like so. So this is measuring in an arbitrary unit from 0 to 833 currently. So what I would like you to do then, your investigation is, again, using Excel. This time you're going to have three columns. You're going to have length. Now I'm going to call these centimeters. I don't think they are, but they'll do for us. We're then going to have voltage, again in volts, and we're going to have current in amps. Okay, and your length. So this time I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. I'm assuming that these here are millimeters on my route. No, what would they be? Hundredths of a centimeter. So these numbers are in hundreds. I could change this. Let's rechange it. Oh, no, wait. So length. Options. We'll leave it like that. So we've got hundreds. Okay, so let's go back to our FET animation. So what we're going to do is line up our ruler so the 0 is on this node and that our wire runs perfectly alongside it. Now there's two options you can have here. So option 1 is what you can do is take your voltmeter, and you can take your voltmeter and leave the black one on the joint at 0 and place the red one at the different lengths like so. And every length, what you'll do in your table is you will record down your current and your voltage. So length 0, both, well, current wasn't 0, current was 0.41. And for length 1, it's 0.54. 0.41. Or the other option you can do is you can move this and you can change the length of the wire as you go along. Personally, I think it's much better to go for this method where you just move the probe along at your different lengths and get onto that. Okay, so off you go. And record your results. Pause the video now whilst you're doing it. Okay, welcome back. So I've taken my results. I went for the fixed length of wire, moving the probe. Now because I have the fixed length of wire, current doesn't change because the current has to flow through this whole length of wire all the time. So for the current hasn't changed. The current's changed slightly from what I had before because my thing has changed length. All we are changing is the length of wire, so our voltage that our wire has, because remember each section of this wire is in series with each other, so each section of this wire will share the voltage and have a different voltage depending on its length. Okay, so I've now got my results. So what do we need to do for these results? What I'd like you to do is to have a column called resistance, Now if you're doing this by hand, you can use the proper symbol for resistance, which is an ohm, capital Omega. If you're doing it on Excel, you can also do that by changing the font to symbol, like so, and it's a capital W. And there we are, so we've got resistance. What I'd like you to do now, remember resistance is voltage divided by current. Drag it down and we get our resistances. Now we don't need all these decimal places, so let's change that. Right click, format cells. We can change them to number. Yeah, 2 decimal places will be enough. So there we go. So we now have our resistances. And the graph we're going to plot this time is we're going to plot length against resistance. So same idea, insert, scatter graph, there's our wire, and we're going to move our chart to a separate page again, and this time you can again add a trend line, set the intercept to 0, display equation on chart, and what this value here is, the 1.3171, gives us an idea of how much resistance per length our wire has. If you really want to chart it up, don't forget we should have our axes labels, so let's do that. And chart element, we want axes titles, so this one is length in centimeters, and our vertical one is going to be resistance in Omega. Now, we'll leave it with a W for now. It won't let us change the font of our axis label, which is a pain. Let us do this right there. So I'll click just on that. Right click font, and I'll go down, find symbol. There it is. Click OK, and it changes just that. There we are. Resistance in Omegas. Okay, excellent. So that's that practical done then. So as you can see, that the longer a wire, the more resistance it has. And if you think about it, that kind of makes sense. We said resistance is caused by all the positives in this wire stopping our electrons going through. So the longer we make it, the harder it is for our electrons to go through. Now, for most of our experiments that we do on here, we turn wire resistivity all the way down to tiny, which basically means that it's 0. Okay, and so here we don't need to worry so much then about the resistance of that wire. It still has some resistance, as you can see by the length of this increasing massively, but also if we add a component like so, like a light bulb, into our circuit, then the resistance of our wire is so tiny compared to our bulb that all the voltage goes onto our components that we're using. Okay, excellent. Thank you very much for watching.